Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 1 lecture. I hope you enjoy it.
This is chapter 4, section 7, 4.7, and 4.7 is optimization. All right. Now, in optimization, well, here's the idea. The idea is to use calculus to maximize or minimize a given scenario. What do I mean by that? Well, we want to use calculus to figure out, given some restrictions, what is the maximum value of a volume, for example, or perhaps given some other restrictions, what is the minimum value of an area? All right, so that's what we want. Now, how are we going to do it? Well, let's think about this. So what we're going to do is we're going to create some sort of function, all right, and that function is going to have a max or a min, all right, and we know how to find those values because, well, this is a critical value, right? And what do we know about critical points? There, for it to be a maximum, it has to go from increasing to decreasing. This is a minimum. That's a critical value. We know that those happen when we're going from decreasing to increasing, right? So that's what we're going to use calculus to solve these. In general, this is what we need. We need an objective function and a constraint function. Essentially, the objective function is, well, given this scenario, what is it that we're trying to maximize? What is it that we're trying to minimize? All right, if we're trying to maximize an area, that's the objective function. If we're trying to minimize cost, that's the objective function. All right, anything that we're trying to maximize or minimize, in general, optimize, that would be our objective. Our constraint, well, we can say, well, what is it that we're restricted by? All right, what are our restrictions within the given scenario? So let's get some examples here. So here we go. The sum of the first number and twice the second number is 108. Find the numbers that would result in a maximum product. Right? So here's what we're saying. We've got the sum of a number and twice the second number to be 108. Given that, what would the numbers be such that their product is the maximum? So what's the biggest possible product there? All right, so here let's think about this. So in here, our objective is to maximize a product, right? And what is a product here? We have a number and a second number. So what we're saying here is that the product is x times y. That's what we're trying to maximize. Our constraint. Well, what are we limited by? Well, we're limited by the fact that there's sum of the first and twice the second. So the first plus twice the second has to be equal to 108. Right? So that's our constraint. We're restricted by that. At this point, well, what do we do? Well, if you recall, I said we were going to be looking for maximums and minimums, right? So essentially there, what we need to do is we want to take the derivative of our objective function. But notice that our objective function is not with respect to one variable. So as written, it is technically not a function. So what we need to do is write it as a function. And how are we going to do that? Well, I want to make sure that everything here is in terms of x. Excuse me. So in here, I'm going to figure out a way to solve for y so that I can plug it in there. So if I solve for y here, what do I get? I get y is equal to negative x over 2 plus 54, right? Move the x over, divide everything by 2. At that point, well, that tells me now that p as a function of x would be x times negative x over 2 plus 54. In other words, negative x squared over 2 plus 54x. And now look at that. Now I've got a product function in terms of just one variable instead of two. All right. So now that we've got that, well, we're trying to maximize that. So what we want to do here is take the derivative. And when we take the derivative, what do we get? Well, I end up with negative x plus 54. And what we're trying to do here with the derivative is we're trying to find a critical value. So how do we find critical values? Set it equal to 0. What does that give me? X is equal to 54. And now that I've got the value of 54, I can figure out the value of y, right? The value of x being 54, I can figure out the value of y. So in here, what does that tell me? That tells me that y is equal to negative 54 over 2 plus 54. Well, negative half of 54 plus 54, that's going to be just half of 54, which happens to be 37. All right, so our y value there is 37. That's not 37, sorry, 27. I need to sound it off. 27. Okay. So our y value is 27. So now we've got the two values, right? And we can verify that this actually holds as far as their sum, right? Because the first number, 54, plus twice the second number, 27. Well, 2 times 27 is 54. 54 plus 54 is 108. Good. So it does pass the constraint. But now, how do we know that we actually found a maximum? All right, because all we did here was we just showed that it was a critical value, that 54. But how do we know that it's a max? So here's how we verify. Verifying. Oh, that's a weird way to spell verifying. Let's try it again. Verification. So what we're going to do here is we're going to well, recall the second derivative test. And I'll scroll back up for the visual here. The second derivative test essentially told us that if the second derivative gives is less than 0, in other words, the concavity is negative, then we have a maximum value. If the second derivative is greater than 0 at that critical value, in other words, the concavity is positive, then we have a minimum. All right. So let's see what we get here. We need to figure out stuff with the second derivative. So if I take the second derivative here, here's my first derivative. So my second derivative would be just negative 1, right? And at that point, since my second derivative is just negative 1, well, negative 1 is less than 0, right? Irrelevant of what I plug in for x, right? X is supposed to be 54 there, but irrelevant of what I plug in there, I get negative 1. So since in here I end up with something less than 0, I end up with a not minimum, with a maximum, because we have a negative concavity. All right. Now, next example. So that was example A. So example B. And example B says the following. Find the point on the graph that is closest to the given point. And here's what we've got. We've got the graph y equals x squared, and we've got the point 2 comma 1/2. All right. So let's see what we're saying here. I'm gonna sketch this. We're gonna get a visual of this right now. Let's see. All right. So this is our visual. We've got some function here, y equals x squared, right? And that's the graph of y equals x squared. And we've got this point over here, 2 comma 1/2, right? That's the height of 1/2. Let's say that this is 2 over here. And in here, we have many different distances to the graph, right? Depending on which path we take. What we're trying to figure out here is, out of all these possible lines here, right, which one is the shortest distance? That's what this question is asking. All right, which of all those lines is the shortest distance? So let's see what our objective then here is. Our objective is to minimize the distance. And what was the distance formula? The distance formula is the square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Right? That is our objective. And what is our constraint? Well, our constraint is that the point that we find, right? The point that we find has to be on this graph. So our constraint is that y must equal x squared. All right. So let's do this. And here in our objective, if I take some generic point here, right? If I take some generic point that's on the graph, for example, this one right here. Well, what are the coordinates of that point? The coordinates of that point are x comma y, right? So our distance equation, our objective equation there, is going to be, well, the distance is equal to the square root of x sub 2, I'm going to call that x, minus x sub 1, I'm going to call that 2, squared, plus y sub 2, I'm going to call that y, minus y sub 1, I'm going to call that 1/2. All right, so that's our distance formula. But notice there that we have that in terms of two variables, x and y. So what we're going to do there is we're going to use our constraint to rewrite this as a function of x. All right, so our distance in terms of x, well, what is that going to be? That's going to be the square root of x minus 2 squared plus the y value is x squared. So x squared minus 1/2 squared, right? And at that point, well, we've got our distance in terms of just one variable, and we know now that to minimize this, to minimize it, we need to find the critical values. So to find the critical values, we must take the derivative. I'm first going to write this as this entire statement, x minus 2 squared plus x squared minus 1/2 squared. I'm going to write that as to the power of 1/2. All right. Let's simplify the inside here a little bit, just so that we're not working with too many chain rules. So if I distribute this, so I have x minus 2 quantity squared, that's x squared minus 4x plus 2, plus this piece squared, that's going to be x to the 4th minus x squared plus 1/4. And all of this raised to the 1/2. All right. Now let's combine like terms here. I see here that this x squared and this x squared cancel each other out, right? And that's all I really see here. So let's combine like terms, and we have here now, perhaps a little here, x to the 4th plus, minus 4x, and then 2 plus 1/4. That's 2 and 1/4. That's the same thing as saying 9/4, right? Oh, hold on. How did I get that 2? This is supposed to be this value squared. That's supposed to be 4. Look at that. 4. All right. 4 plus 1/4. There we go. It's 4 and 1/4. That's 17/4. So we have plus 17/4, and all of this to the 1/2. All right. So that's our distance formula. Still. Now let's figure out the derivative, right? So we can figure out the critical values of this. So if I take the derivative of that, what do I get? I end up with 1/2 times x to the fourth minus 4x plus 17/4 to the negative 1/2 times 4x cubed minus 4, right? And essentially this I can rewrite as, well, this in here I can factor out a 4, right? I'm left with x cubed minus 1, and then this 2 and this 4 reduce. So what I end up with here is really 2 times x cubed minus 1 over x to the fourth minus 4x plus 17/4 to the 1/2, right? Now, that's our derivative. And what do we want to do with this? We wanted to find the critical values. So how do we do that? We set this equal to 0. And look at that. We've got a fraction equaling 0. When we've got a fraction equaling 0, that can only happen when the numerator itself is 0. So 2 times x cubed minus 1 is equal to 0. Divide both sides by 2. X cubed minus 1 is equal to 0. Move the 1 over. X cubed is 1, which tells us that x is equal to 1. So now we've got the value of x, all right? And now that we've got the value of x, we can figure out the y value, since we know that y is equal to x squared. So in this case, I end up with y is equal to 1 squared, which is 1. So what did that tell us? What we just found is that the closest point is 1, 1. All right, that's the closest point to the given value. So in other words, in here, we've got some point here, maybe this one right here. That one right there is 1, 1. And that would be the shortest distance, or the shortest line that we could create from that point to 1/2 to the function. All right, that's what we found there. And well, how do we know that that's actually the value? Well, I spoke about the second derivative test in the previous example, but in here, finding the second derivative seems kind of annoying, right? It seems kind of annoying because we had to do the quotient rule here. But we know there's another way to figure out whether something's a maximum or a minimum, and that would be to use the first derivative test. So let's do the first derivative test for this one, and we're going to be plugging them into d prime of x, and we're testing around a critical value of 1. To the left of it, we can test something like 0. To the right of it, we could test something like 2. And we're plugging this into our first derivative. Now, let's see what happens here. If I plug in 0, on the bottom I just get 17/4 to the 1/2. That's some positive value. I don't care what it is, it's just positive. On the top, 0 minus 1. Well, 0 cubed minus 1 is negative 1. And I have a negative on top and a positive on the bottom. Overall, that's a negative. Tells me at that point it is decreasing. Let's plug in 2. 2 cubed. 2 cubed is 8 minus 1 is 7. That's a positive value, so the numerator is positive. Now let's figure out the denominator. All right. 2 to the fourth. 2 to the fourth is 16. 4 times 2, 8. 16 minus 8. 16 minus 8 is 8. 17/4 is 4 1/4. So 8 plus 1/4, that's a positive value. To the 1/2, still a positive value. So in here, we end up with this side, everything being positive, so it's increasing, which tells us, right, we're going from decreasing to increasing, we have a relative minimum. All right, we have a relative minimum. So that's another way to verify that you actually optimized it the way that you needed to. We've got that it was actually a relative minimum. All right. Let's do another one. Let's do a similar one. Same instructions. We're finding the closest point to the curve or to the graph. And here I've got y equals radical x, and I've got the point 4, 0. All right. Cool. So let's get the visual for this one. I'm gonna do this again. Well, perhaps I'll choose the colors this time. This is in yellow, and this is in blue. All right, cool. So what do we have? We've got this graph, radical x, and that's what that looks like, radical x. And we've got this point, 4, 0. And the question here is, well, we've got a whole bunch of different distances that this point could be from the curve. The question is, which of these is the smallest distance? Like, which of these points provide the smallest such distance there? All right. And in here, well, same exact idea. Let's say, for example, that this point right here, the generic coordinate there is going to be x comma y, right? So if we look at our objective is the same. Objective is the same as the last example. In other words, it is the distance formula, which is x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. Our constraint, well, this time our constraint is that we must be on this function, radical x. So our constraint is that y must equal radical x. All right, so let's see how this one works. We need to rewrite our distance function, and if I apply it to these 2 points, remember this is 4 comma 0. If I apply it to these 2 points, what do I get? I get x minus 4 squared plus y minus 0 squared, right? X minus x sub 2 minus x sub 1, y sub 2 minus y sub 1. Which, in this case, what does that mean? Well, we know the y value. The y value is radical x. So I have the square root of x minus 4 squared plus radical x minus 0, well, that's nothing, so squared. I'm going to rewrite this as, well, let's expand the entire denominator, the entire inside there, and see what we get. We get x squared minus 8x plus 16, right? That's the first piece. And the second piece is just x, and all of this to the 1/2. In other words, x squared minus 7x plus 16 to the 1/2, right? That negative 8x and this positive x, negative 7x. But that's just my distance formula with respect to x, right? Just the distance formula with respect to x. So what we want to do here is we once again want to take the derivative because we want to find the critical values, right? We're trying to minimize this distance. And if I take the derivative here, what do I get? D prime of x ends up being, well, 1/2 times x squared minus 7x plus 16 to the negative 1/2 times 2x minus 7. All right, in other words, what we have here is really 2x minus 7 over 2 times x squared minus 7x plus 16 to the 1/2. Right? Now, all we found there was our derivative because we wanted to find the critical value. And how do we find the critical value? We set this equal to 0. And look at that. We've got a fraction equaling 0. The only possible way for a fraction to equal 0 is if the numerator itself is equal to 0, giving us the value for x as being 7/2. All right. So now we've got the value of x, 7/2. So what's the value of y? Well, recall that y was the square root of x. So in here, y is going to be, let's do it as 7/2. Well, let's do the square root of 7/2. I'm going to rewrite this as radical 7 over radical 2, just so that I can rewrite it again as radical 17 over 2 by rationalizing it. All right. So in here, what we found is that the coordinate is 7/2 comma radical 17 over 2. All right, that's the coordinate. That's the answer. And how do we verify it? Well, we're once again going to, well, let's see. In here, again, it's easier to do the first derivative test than the second derivative test, right? So it's easier to just go ahead and test around our critical values than it is to take the derivative. So we're going to verify by testing around 7/2. And we're testing it into the derivative. 7/2 is 3.5, so we can plug in things like 0. We can also plug in things to the right like 4. Now if I plug in 0, what do I get? On the top, 2 times 0 is 0, 0 minus 7 is negative. So on top it's negative. On the bottom, 0, 0, positive 16. 16 to the 1/2 is positive. The bottom is positive. So the top was negative, the bottom is positive. Overall it's negative, decreasing. Plug in 4. 2 times 4 is 8, minus 7 is 1. That's positive. On the bottom, 4 squared. 4 squared is 16. 16 plus 16, ooh, 32. And then I have negative 7 times 4. Negative 7 times 4 is 28. And I had 32 minus 28. That's positive, right? It's 4. Doesn't matter the value, the actual values, that is positive. So we had positive on top, positive on bottom, overall positive. It is increasing, which tells us relative minimum. So that tells us we actually did minimize the distance. All right. All right, let's kick it up a notch here. Let's say that we had all right, so example D. What are the dimensions of the largest rectangle that fits in the top half of the ellipse x squared over 64 plus y squared over 9 is equal to 1. All right, so we're looking for those dimensions, for the dimensions of the largest rectangle that fits in the top half of that ellipse. All right, so let's see what we have here. This ellipse here looks as follows. This is 3, this is negative 3. That's based off of the square root of the bottom there. This is 8. This is negative 8. That's based off of the bottom of x squared. And the ellipse here, which I'll do in blue, looks as follows. Something like that, right? And what we're trying to figure out here is the largest rectangle that fits on the top side of this, on the top half, right? So that means we're looking for something like this, the largest rectangle in here, all right? The largest rectangle that fits there on the top half. Now, can I center this a little bit better? I guess it's a little bit better. But anyway, now in here, let's see. Well, we need to come up with some sort of objective and some sort of constraint, right? Now, notice here that I said that it needed to be the top half of the ellipse. So essentially, we don't care about this bottom piece at all. In fact, I'm going to erase it. We don't care about the bottom piece. We care about that rectangle inside the top half. Now, that top half is given by, well, if I solve for y here in this equation, I end up with the following. So I have, well, move this piece over. So I have y squared over 9 is equal to 1 minus x squared over 64, right? If I come up with a common denominator on the right, I have 64 minus x squared over 64. All right, multiply by 9 on both sides, so y squared is equal to 9 over 64 times 64 minus x squared. Take the square root of both sides, y is equal to plus or minus 3/8 times 64 minus x squared to the 1/2, right? From there to there, all I did was take the square root. But I'm looking for this piece that's on top. This piece on top of the ellipse here, that is represented by the positive version of this y value. So we're going to say here y is equal to 3/8 times 64 minus x squared to the 1/2. Notice that what we essentially found here is this is the constraint. Why is that the constraint? Well, because we must be within the ellipse, right? Within the top half of the ellipse. That's our constraint. We must be within this ellipse. Now, what is our objective? We're trying to find the dimensions of the largest rectangle. The largest rectangle. What do I mean by that? We're looking for the largest area of that rectangle. All right. And now let's see. Well, what is the area of this rectangle? Let's think about it. Let's think about this point right here. This point right here is at x comma y, right? That means that this distance is x, and this height is y, right? Giving us that essentially here, well, y is the width of the rectangle, whereas the length of the rectangle is 2x. So our objective is to maximize that area, right? So we want the largest rectangle. So it's the area is equal to length times width. That's the area of that rectangle that we're trying to maximize up here. And what was L? L was 2x. And what was W? W was y. So our area function is 2x times y. But that's not in terms of one variable. So let's go ahead and change it in terms of one variable. I'm going to plug in the y definition that we had over here from our constraint. So what we get now is 2x times 3/8 times 64 minus x squared to the 1/2. Reducing this, right, this fraction here, I can just simply say that it's 3x over 4 times 64 minus x squared to the 1/2. All right. So that right there is my objective function. And what was the objective? We want to maximize this area. So again, to find the maximum value, we need the critical value. So to find the critical value, we're going to take the derivative. So a prime of x would be, well, look at this. I've got a product of two functions, so I need to do the product rule. So the derivative of the first, 3/4, times the second, 64 minus x squared to the 1/2, plus the derivative of the second, 1/2 times 64 minus x squared to the negative 1/2 times negative 2x times the first, 3x over 4. All right, so that's our function there. All right, we need to set this equal to 0. So let's actually simplify this first. All right, and how can we simplify this? Well, I see here that there's a 3/4 there and a 3/4 there, right? What else do I see? I see that we have a 64 minus x squared, and perhaps I'll do it in red. A 64 minus x squared and a 64 minus x squared. What else do I see? I see that this 2 right here cancels out this 2. So what are we left with? Okay. Let's see. If I want to factor out those things, well, I'm going to factor out a 3/4, and I'm going to factor out 64 minus x squared to the, well, between negative 1/2 and positive 1/2, the negative 1/2 is the smallest of the two, so that's what I will factor out. And what are we left with? This 3/4 was taken out. The 64 minus x squared, we took out negative 1/2. So I had 1/2, took out negative 1/2, I'm left with 1. Right, because 1/2 minus negative 1/2 is 1/2 plus 1/2. That's how I'm left with 1 in the numerator, excuse me, in the exponent. Plus, what are we left on the other side? 1. Well, 1 times anything, we don't really write it. 64 minus x squared to the negative 1/2, that's what we factored out over here. Ooh, x squared, look at that. X squared. All right. This negative, we never took it out. This x, we never took it out. These 3/4 we took out, but this other x we didn't take out, so we have plus negative x squared. All right. And how can we rewrite this? I'm going to rewrite this as 3 times 64 minus 2x squared, right? This negative x squared and this negative x squared is negative 2x squared, over 4 times 64 minus x squared to the 1/2. Negative exponent goes to the bottom. At that point, now we're going to find our critical value, which means we must set this equal to 0. All right. So if I set it equal to 0, what do I get? I've got a fraction equaling 0. The numerator itself must be equal to 0. Divide both sides by 3. Move the 64 over. So I've got 2x squared is equal to 64. Therefore, x is equal to 30. Well, excuse me, x squared is equal to 32, giving us that x is equal to plus or minus the square root of 32. In here, I'm going to ignore the negative because the way that we defined the x over here, it was this positive distance, right? It was on the positive side of the x-axis. So we're going to say this becomes just, well, square root of 32. 32 is 16 times 2, so it's going to be 4 radical 2, right? This is square root of 16 times 2. The square root of 16 is 4. And again, we're using the positive value because this x represents a distance, right? Now, what does that tell us? Well, that tells us that the length of the rectangle, well, if you recall, the length was twice x, which in this case means 8 radical 2. And the width of the rectangle, recall that was y. And what was y? By definition, y was this thing over here. Let's copy that. So I'll just put this on the side here as a reminder. All right. So that was a y value. So in this case, that's going to mean 3/8 times 64 minus 8 radical 2. Well, no, that's not x. What was x? X was 4 radical 2. Sorry. I'm actually going to use just radical 32. Radical 32 squared, and all of this to the 1/2. Radical 32 squared, that's just 32. So I have 3/8 times 64 minus 32 to the 1/2. 64 minus 32 is 32. So 3/8 times 32 to the 1/2. 32 to the 1/2, we already know it's 4 radical 2. So I have 3/8 times 4 radical 2, which reduces to, well, the 4 and the 8 reduced. So I have 3/2 radical 2. Now let's write that a little bit different. 3 radical 2 over 2. All right. So that's our width. All right. So our dimensions were, so if I say length times width, that's going to be 8 radical 2 by 3 radical 2 over 2. All right. Now, how do we know that that actually is the maximum area? Well, again, we can either do the first derivative test or the second derivative test. In this case, let's look at our derivative. This is the derivative. If I want to do the second derivative test, it requires me using the quotient rule and having a very complicated derivative. So instead, we're just going to use the first derivative test. So we're going to verify using that. And we're going to plug this into f prime of x, and we're going to test around our critical value, which was 4 radical 2, right? And just for reference, 4 radical 2, I forgot what value it was. Give me a second. 4 radical 2. It is approximately 5.66. All right, approximately. So we need to test around this value of 5.66. All right, well, to the left of it, I'm just going to test 0. To the right of it, what can I test? Well, something bigger than 5.66 will be something like 6, right? And we want to test this into the first derivative. So I'm going to go ahead and copy our derivative here, just so that we can keep it in mind what we're testing into. So, and I'll change the color of that. All right, so that right there is the, I shouldn't be putting f prime, I should be saying a prime. A prime. So a prime of x is equal to that. All right, cool. So in there, we're going to test 0. Plug in 0. The bottom, positive, right? Because 64 minus 0 is positive. Square root of 64, positive. On the top, 0 times 2 is 0. 64 minus 0, positive. So everything on top and bottom was positive. So I have positive, meaning that we're increasing. Plug in 6. 6 squared, 36. 64 minus 36, doesn't matter. It's positive. The square root of a positive value, it's positive. On top, 6 squared, 36. 2 times 36, negative 72. Excuse me, 72. 64 minus 72, that's negative. So we have, well, and then negative times 3, that's negative overall. So on the top it's negative overall, on the bottom is positive overall. So negative over positive, negative, which means it's decreasing. And now we're going from increasing to decreasing, right? So that has to be a relative maximum, which is good because we were looking for the maximum area here, right? We're looking for the maximum area. So this is essentially our answer. All right, the dimensions of that rectangle. All right, so that was D, right? I think that was D. I like to keep a track of the lettering. D. E. Next one is E. All right, let's complicate this a little bit more. Let's do a little bit harder examples. A rectangular solid and perhaps I'll shift this a little bit down so it doesn't. There we go, way better. A rectangular solid whose base length is twice its base width has a surface area of 675 square centimeters. Find the dimensions that will result in a solid with maximum volume. All right. Another way of thinking about a problem like this, well, first I'll reread it. It says a rectangular solid whose base length is twice its base width has a surface area of 675 square centimeters. Find the dimensions that will result in a solid with a maximum volume. Okay. Another way of thinking of a problem like this is sometimes they'll phrase it as you have 675 square centimeters of material. Find the maximum box that you can create for that, or the dimensions of the box with the largest volume, given that its base length is twice its base width. All right, or something like that. But the idea is the same. So in here, let me start with a visual. And the visuals are always super helpful to figure out what's going on. All right. And what do we have here? Rectangular solid. So a box, essentially. A rectangular solid whose base length is twice its base width. All right. So let's see how we're going to draw that. And I guess this is pretty good. There we go. That's a rectangular solid. And here's the width. Here's the base. Which means here's the base length, here's the base width, and here's the height, right? What we know is that the base length is twice the width, all right? And well, let's see. What is our objective? The objective is to maximize the volume. So what's the volume of this? The volume is length times width times height, which in this case, well, we know the length is 2w, so we have 2w times height. So we've got we've got the volume being 2w squared times h. Let's put that on the side for now. That's going to be our objective. Let's figure out our constraint, how our constraint is going to help us here. And perhaps I'll move this out of the way there. I'll put it down here for now. So that's not how you spell objective. I'm missing like a C there or something. Objective. All right, cool. Constraint. Our constraint is, well, what must hold true about this rectangular solid? What must hold true is that the surface area is 675 square centimeters. So the constraint is the surface area. So let's figure out what the surface area normally is. The surface area is the area of all the sides added together. So in here I have this one and this one are the same, right? So twice of that. So twice the area of the side, which was W times H, plus the bottom and the top. So there's two of those which are the same. So it's going to be twice the bottom, which, well, what is the area for the bottom? Length times width. Length times width. And then plus the front and the back. The back is kind of hard to draw there. But this front one happens twice, right? In the front and the back. So we have twice the length times the height. Alright, let's rewrite this a little bit. They all have a 2, so I can factor out a 2. And I'm left with, well, what else do we have? We have that L is equal to twice W. So we have WH plus, I factor out this 2, L is twice W times W, and W squared, plus L was twice W, and then that times H. Alright, now we have here WH and WH. We can combine like terms here, so I have 2 times 3WH plus 2W squared. And if I really wanted to here, and we really want to, is distribute this 2. So 2 times 3, so I'll write it as 4W squared plus 6WH. So that's a surface area formula. But what do we know about the surface area? Well, we know that it has to be, what is it? 675. It has to be 675 square centimeters, right? And what I want to do here is I want my volume function to be in terms of just one variable. Right now I have it in terms of 2 variables, right? We want just one variable so that we can take the derivative. So in here, what we're going to say is, well, I'm going to solve for H so that I can replace this H, right? I don't want to solve for W because, well, that's going to be kind of annoying here. But H is super easy to solve for here. So let's see what we get. We end up with 6WH is equal to 675 minus 4W squared. Divide both sides by 6W. So H is 675 minus 4W squared over 6W. And now we got a value of H. So now we can definitely figure out the volume of this box with respect to the height. So it's going to be 2W, not with respect to the height, with respect to the width, right? Because our variable is W. So 2W squared times 675 minus 4W squared over 6W. And at this point, we're going to say, well, let's reduce this. The W and the W cancel each other out. The 2 and the 6 reduce, right? And what am I left with? I'm left with W over 3 times 675 minus 4W squared. Distributing this W over 3, well, what do I get? I end up with 675W over 3 minus 4/3 W squared. And that's a 3 down here. 675W over 3. 675 divided by 3, that actually reduces. This becomes 225W minus 4/3 W squared. All right, 675 divided by 3 is 225. All right, so now that is my volume function with respect to W. What I need here is a critical value for that function, and what we know is that those happen at the derivative, where the derivative is equal to 0. So first I must find the derivative. The derivative here is 225 minus 8/3 W, right? And hold on, I just realized I made a mistake, and I realized because that didn't make sense to me. W times W is W cubed, not W squared. So here, this is also W cubed. I already had a W cubed. All right. And if I take my derivative, well, the first part was correct, 225. But the next part, the derivative of that, Bring the 3 down to the 1/3, and the 1/3 cancel each other out, right? Bringing the 3 down. I end up with 4w squared. All right, there we go. Way better. So that is my derivative. So now what I need to do here is figure out my critical values by setting it equal to 0. And in here, solving for w squared, I end up with w squared is equal to 25 over 4, right? Move the 225 over, divide by -4. At that point, that tells me that w is equal to, technically, plus or minus the square root of 225 over 4. Well, the square root of 225 is 15. The square root of 4 is 2. In here, this width is a distance, so I'm going to go with 15 halves. And we were given units, right? We were given centimeters as our units. So our width is 15 halves centimeters. All right. Our length was twice the width. So that's going to be 15, excuse me, let's do it as 2 times 15 over 2, which is going to give us 15 centimeters. And our height was, well, we had a complicated thing for the height. Where is it? It's over there. So let's go ahead and copy this so that we can reference it as we're plugging it in. And I'll change the color of that. All right. So in there, our height, what are we going to get? Plug in 15 halves for w. All right. So we have here 675 minus 4 times 15 halves squared over 6 times 15 halves. All right, on the numerator, 675 minus 4 times 15 squared is 225. 2 squared is 4. These 4's reduce. 6 and 2 reduce, so I have 3 times 15 is 45, right? That's a 3 here. All right. Now, 675 minus 225. Well, 600 minus 200 is 400, and 75 minus 25 is 50, so I get 450 over 45, giving me, well, simply 10, and our units were in centimeters. All right, so now we know that our dimensions are, well, if I write it as length times width times height, it's going to be the length we had 15 centimeters by the width was 15 halves centimeters. You could think of that as 7.5 centimeters. I know in general I don't like decimals, I prefer fractions, but when it comes to word problems and an actual real life value, I'm okay with them. So length times width times height, our height was 10 centimeters. So that is technically the answer, the dimensions of the box or the rectangular solid. But now, how do we verify? So how do we check? Well, again, we have two ways of doing it. First derivative test or the second derivative test. In here, I'm going to go ahead and just take the second derivative because it's quicker than doing the first derivative test. And if I take the second derivative, right, our first derivative being this statement, well, the derivative of that is negative 8w, okay? So our second derivative with respect to w was negative 8w. Since w was, what do we have for w? 15 halves, right? The width, 15 halves. So if I plug in 15 halves, or 7.5, but I'll write it as 15 halves, and I plug it into here, it doesn't matter what the actual answer is. The point is that it's negative. It is less than 0. Because it is less than 0, we have a negative concavity, which is facing down like that, right? Which means that our critical value is a relative max, which is good, right? Because we were trying to maximize the rectangular solid. So next example. So that was F. So let's get a similar problem, but a rectangular storage container with an open top is to have a volume of 10 cubic meters. All right. The length of its base is twice the width. Material for the base cost $10 per square meter, and material for the sides cost $6 per square meter. Find the dimensions of the box, of the cheapest box, or the cheapest such container. All right. So here we go. Noticing here that we're also working with a rectangular like a rectangular solid, right? So here's our visual. Our visual is that we've got a rectangular box, right? So something like this. And what we're trying to do here is we're trying to minimize the cost of this box. All right, and what do we know about this box? We've got that this is the length, this is the width, this is the height. All right, the length is twice the width. All right, so that's similar to the last problem, but here's where this is different. In here, we've got an open top. All right, so that means that we're not going to consider the top of this box when we're trying to come up with our optimization problem here. Now let's look at the constraint that we're given. All right, the constraint that we're given is for the volume, right? Because it has to have a volume of 10 cubic meters. So the constraint here is, well, the volume, which is length times width times height, has to be equal to 10 cubic meters. But we know that the length is twice the width. So in here, what we end up with really is that 2w squared, right? Because L is 2w, and 2w times w is 2w squared. So 2w squared, h, is equal to 10, giving us that h is equal to 5 over w squared, right? Divide both sides by 2w squared. 10 divided by 2 is 5. So that's our constraint. Now let's look at our objective. And what was our objective here? The objective was to minimize the cost. So we have to come up with some sort of cost function. Now, what do we know about the cost for this? All right, we know that the base costs $10 per square meter. All right, so what does that mean? That means that the cost is going to be $10 times, well, let me do it this way. The cost was $10 per square meter for the base, and the area of the base is 2w squared meters squared. Notice here that those square meters cancel each other out. So that's just for the base. But what about the sides? Well, let's look at this. We have 4 different sides. Well, we have 4 sides. 2 of them, the left side and the right side, those 2 sides have the same area. And what was the cost for the sides? The cost was $6 per square meter. All right, so we're going to have this is for left and right. So here maybe I should say that this was for the base. This is for the left and right. So left and right. And that was $6 per square meter times the area. Well, the area is WH, but we have 2 of those. So twice WH meters squared. And in here, again, we see that the square meters cancel each other out. So that's the left and right. Now, the front and back. The front and back is still technically part of the sides, right? So in here, we're going to say, well, that's going to be $6 per square meter times, well, we have two of those, so times 2, times the area of one of these. So this area here, well, is the length times the height, and the length times the height means 2W times h, and these are meters squared, right? And just like before, the square meters cancel each other out. All right, so let's see what we really have here. Our cost now is going to be, well, 2 times 10 is 20, so 20 W squared plus 6 times 2 is 12, so 12 WH plus 6 times 2 times 2. 6 times 2 is 12, times 2 is 24, so 24 WH, right? And notice that the units left in every single one of these was dollars. So it's just a straight up cost. Now, I'm going to ignore that for now. So what we have now is that the cost is 20 W squared plus 36 WH. Now, at this point, well, we have the cost in terms of two variables, W and H. But I know what H is. From our constraint, H is 5 over W squared. So what we're going to say now is that this becomes 20 W squared plus 36 W times, what was it, 5? 5 over W squared. Yeah, 5 over W squared. So that gives us, well, let's simplify that a little bit. Well, I'll go on the next slide. So now what we have here is that the cost in terms of W is 20W squared plus, in here, this W cancels one of those out, so I end up with just over W. And then 5 times 36. Well, 5 times 30 is 150. 5 times 6 is 30. 150 plus 130. Excuse me, 150 plus 30 is 180. So now I've got my cost function. All right. And the next thing we want to do here is, well, we're trying to minimize the cost, right? Because we're trying to find the cheapest box here. So we want to minimize the cost. So what we're going to say here is, well, we want to find the critical point. And to do that, we have to take the derivative. So we said we end up with, well, the derivative here ends up being 40W minus 180 over W squared. All right. So all I did there was take the derivative of each of those, right? You can think of this as 180 W to the negative 1, right? Bring the negative 1 to the front, subtract from the exponent. All right. Now, at this point, well, since we're looking for critical values, I'm going to set this equal to 0. Move this piece over. I end up with 40W is equal to 180 over W squared. Multiply both sides by W squared, divide both sides by 40. I end up with W cubed, right? W squared times W is W cubed. Is equal to, if I divide both sides by 40, I end up with 180 over 40. 180 over 40, they're both divisible by 10. So 18 over 4. 18 over 4, they're both divisible by 2. So I really have that W cubed is equal to 9 halves. All right. Which tells me now that W is equal to the cube root of 9 halves. Whatever that happens to be. All right. Is the cube root of 9 halves. In fact, if you really want to know, this is approximately 1.651. But we like non-decimals. So that's our width. Well, knowing the width, I can figure out the length, right? Because the length is twice the width. So that means the length is 2 times the cube root of 9 halves. And, all right, now what's my height? The height, if you recall, was, what was it, 10 over W squared? 5 over W squared? 5 over W squared. So we have 5 over our width, which was cube root of 9 halves squared. All right. Technically, we're done, but I want to simplify these numbers a little bit just so that they look prettier. In here, this is really saying 2 times the cube root of 9 over the cube root of 2. If I multiply by the cube root of 2 squared over the cube root of 2 squared, the reason I'm doing that is because I have the cube root of 2. I want to get a perfect cube here. So I multiply by the cube root of q squared. And what do I get? Well, on the top, I have 2 times the cube root of 36. How did I get 36? 2 times 2 is 4. 4 times 9 is 36. Over the cube root of 2 times the cube root of 2 squared. Well, that's going to be the cube root of 2 times the cube root of 4. 2 times 4 is 8, so I have the cube root of 8, which is 2. So these two cancel out, so I just end up simply with the cube root of 36. Alright, and that doesn't simplify anymore, we can just leave it as that. Alright, so now for the height. In here, well, the first thing I'm going to do is rewrite this as 5 over 9 halves to the 2/3. How did I get that? The cube root is the same thing as saying to the power of 1/3, and then I have 9 halves to the 1/3 squared. That's 9 halves to the 2/3. Alright, this is the same thing as saying 5 over 9 to the 2/3 over 2 to the 2/3. Right? And in here, I'm dividing by a fraction, which means multiply by the reciprocal. And in here, I really want to rationalize this. I don't want to have this 9 to the 2/3 down here. So I'm going to multiply this by, well, let's see. Let's see what we have here. I'm going to multiply it by 9 to the 1/3 over 9 to the 1/3. Why am I choosing that? Because now in the bottom, 9 to the 2/3 times 9 to the 1/3 is just 9. On the top, in here, 2 to the 2/3, that's the same thing as saying 4 to the 1/3. How come? Because this is really saying 2 squared to the 1/3, giving me now that I can rewrite the numerator as 5 times the cube root of 36, right? Because in here I have 4 times 9 is 36, and both of them are to the 1/3. So there we go. We've got our length and width and height. So I'll write them over here. So our length by width by height is equal to, well, what was it? Cube root of 9 halves. Let's rewrite that. The cube root of 9 halves we already know to be cube root of 36 over 2. All right. Perhaps I'll put it over here. So that's equal to the cube root of 36 and then everything over 2, right? That's what we found here. I just have an extra 2 here, right? So if I were to ignore this 2, we would still have all of this left, and that would be just the cube root of 9 halves. All right, but I'll take this out. So that's our length, that's our width, right? So our length times width times height is going to be the cube root of 36, and we were in meters, right? By the width, which was the cube root of 36 over 2, cube root of 36 over 2, by the height, which was, and this is also in meters, by the height, which was 5 cube root of 36 over 9. All right. And in here, if you actually do multiply these out, you would see that you get exactly 10 cubic feet. All right. The cube root of 36 times the cube root of 36 times the cube root of 36 is just 36. 2 times 9 is 18. 36 over 18 is 2. 2 times 5 is 10. All right. Now, how do we know that we have, so that's actually the answer to this question, right? Because we were just asking for the dimensions. How do we know that this is actually a minimum, right? So, because we're trying to minimize the cost. So what we need to do here is, well, let's see, here's our cost function. We had two ways of doing it, right? We had doing the first derivative test or the second derivative test. In this case, I'm going to do the second derivative test because that's easier than plugging in our critical value, right? Or testing around our critical value of the cube root of 9 halves. So let's see what we get. So if that's our first derivative, what's our second derivative? So C double prime of W would be, well, the derivative of 40W is just 40. The derivative of negative 180 over W squared. Again, think of this as saying negative 180 W to the negative 2. So if I take the derivative there, I'm going to have a positive 360 W to the negative 3, in other words, over W cubed, right? And now, in here, well, what was our value of W? Our W, our width here, was the cube root of 9 halves, which is approximately 1.6. Okay. Why do we care about that? If I plug in a positive value down here and I cube it, it's positive. 360 over a positive value, that's positive. 40 plus a positive value, in general, this is positive. So what am I saying? What I'm saying here is that c double prime of the cube root of 9/2 is greater than 0, which tells us that we have a positive concavity, which implies that we have a relative minimum at our critical value. All right. So there we go. Those were the dimensions. Now let's say that we ask here, what is the cheapest cost? What is the cheapest cost? Well, at that point, all we need to figure out is what happens when we plug in our critical value, which was cube root of 9/2, into our cost function. I'm going to skip the details of that. I'll leave that up to you because all we're doing is plugging in the cube root of 9/2 into here. All right. But I will tell you what it is. The cost is approximately $163.54. All right. All right. So that is the end of this section 4.7. All right, optimization. But again, it essentially comes down to what I said at the very beginning, which is that we need an objective function and a constraint. All right. The objective is, what are we trying to maximize? What are we trying to minimize? The constraint is, what are we restricted by? All right. Are we restricted by a fixed sum, like it was on this one, right? We were restricted by a fixed sum. And the next one, what were we restricted by? We were restricted by being on the graph, right? Our constraint was y equals x squared. That was the same thing for the next example, by the same idea. And here, what are we restricted by? We must fit inside of the ellipse, right? And E, what were we restricted by? Well, we had a fixed surface area. And the last one, well, actually no, in this one, yeah, in the last one, we were restricted by a fixed volume. All right. So it's always figure out what the constraint is, right? What are your restrictions? And figure out what your objective is. What are you trying to maximize and what are you trying to minimize? All right. So yeah, so that's the end of 4.7.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.